Welcome. In this lesson, we will extend what we learned about computing probabilities for a randomly sampled individual from a normal population, and now focus on sampling several and perhaps many individuals from a normal population, or a population that meets a sufficient size. And we'll talk about that idea towards the end of the video. Now, in these cases where we are sampling from several and perhaps many individuals from the population, as opposed to our previous videos where we just were looking at a randomly sampled individual. So previously it was just an individual. Now as you read through the phrasing of the problems, it will say we've got a sample size of some number. So instead we're sampling many individuals. In that case, when we have many individuals, we need to introduce a bit of new notation specific to sampling many individuals. So we're going to let this X bar over the top, that's our sample mean. And the size of the sample that we're drawing is n. And the population that we're drawing from has a mean mu and a standard deviation sigma for individual that was sampled. Now, in order to extend this idea of the mean and the standard deviation to now our sampled population, we introduce the notation mu subscript our x bar and sigma subscript x bar. Now, it turns out that the mean of the sampling distribution, our mu sub x bar, is just equal to the mean of the regular distribution. However, for the standard deviation of the sample distribution, that is our sigma sub x bar, and it can be found by taking the standard deviation of the distribution and then dividing it by the square root of the number of individuals that we're sampling. And this sigma sub x bar is sometimes called the standard error of the mean, so be aware of that notation. Now in our next example, it says a population has a mean 25, standard deviation 6. We're asked to find mu sub x bar and sigma sub x bar for a sample of size n equals 25. Round our answers to one decimal place if needed. Well, right off the bat, we know mu sub x bar is just equal to mu. So for us, that is 25. Sigma sub x bar is sigma divided by the square root of n, which for us, our sigma is 6. Square root, our sample size n is 25. So this is 6 over 5, which when we type that into the calculator, we'll get a 1.2. Now this next idea is one of the most important concepts in statistics. It is called the central limit theorem. What it says in general is for any population that we're looking at, if the sample size is large enough, and in this case large enough means our sample needs to be greater than 30, then the sample mean, what we were just dealing with in our previous example and discussion, will be approximately normally distributed. So let's take a moment to pause there. We started with just any population, not a normal population. But the central limit theorem tells us if our sample size is large enough, if it surpasses 30 individuals, then we're guaranteed this sample mean x bar is normally distributed. And once we have a normally distributed set, we can always transfer things using our z-score into the standard normal score. And then we can use our chart to identify the probability that we could select something that's maybe less than a certain value, greater than, or between. Now, if we're dealing with this sample mean, our x bar, we've got more than 30 items in the data set, then we know it could be normally distributed. And the mean of x bar is mu, and the standard deviation sigma of x bar is sigma over the square root of n. Now, one thing to note is this cutoff for being greater than 30 only applies if it's just a general distribution. If you're told the distribution you're looking at is already normal, then the sample mean will be normal for any sample size, even if we're looking at a sample size less than 30. So pay special attention to the wordings of the problems. So it says a sample size of 5 will be drawn from a normal population with a mean 60 and a standard deviation of 12. The first question is it appropriate to use the normal distribution to find the probabilities for our sample mean x bar? Now, I'd encourage you to take a moment and read through the first sentence of the example again. Is there any key words that we should take note of? Now, initially you might say, well, the sample size was supposed to be greater than 30, and this is 5, which is less than 30. But actually that doesn't apply here because we're told the population's normal. And if the population starts off normal, our sample size doesn't matter. The sample mean will be normally distributed. So in this case, even though our sample size is small, since we have a normal population to begin with, it is appropriate to use the normal distribution here for our sample mean. So since it's appropriate, let's continue on to B. It says find the probability that our sample mean will be between 50 and 70. Now the sample mean, remember, does not have the original mean and original standard deviation. Instead, once you're dealing with the sample mean, you immediately need to find mu sub x bar, so the mean for the sample mean, and sigma sub x bar. Now, mu sub x bar is just mu, so in this case, no calculation needed. We can read from above the original mean was 60. However, our sigma sub x bar is sigma divided by the square root of n. Here, our standard deviation is 12, and our sample size is 5, so this will be 12 over the square root of 5. And let's round these to 2 decimal places, so our sigma sub x bar, when rounded to 2 decimal places, will round to 5.37. So keep in mind, this is a small context clue. If you are dealing with our previous lessons, it said wording like, what's the probability that a randomly drawn individual would be between 50 and 70? In that case, if it's a randomly drawn individual, that's back to our earlier lessons, and you can just find the z-score from the original mean and standard deviation. However, here, if it says find the probability that the sample mean or x bar is something, then you can only find the z-score once you've found mu sub x bar and sigma sub x bar. So those are going to be small variations in how the problem's worded, and you need to pay attention to those so you'll know how to proceed with the problem. So now that I've got my mu sub x bar, sigma sub x bar, I can start to find my z-scores for 50 and 70. Once I have the z-scores, I can go to the chart, and once we go to the chart, we just take the larger area value minus the smaller area value because that's how you work with the between problems. So we set up our z-score, it's the value minus mu sub x bar divided by sigma sub x bar. So for 50, whenever you type this into the calculator, you'll get negative 1.86 as the z-score for 50. The z-score for 70, similarly, when you calculate it, is 1.86 when rounded to 2 decimal places. And now that I have the z-score, I'm going to go to my cumulative normal distribution chart, and I will identify how much area lies before that in the curve, or equivalently, what's the probability that we have a value less than 50 or less than 70, and we'll record that below. So here for negative 1.86, we look in the chart, and we see that the probability that we have a value before that is 0.0314. And now for positive 1.86, we see the value is 0.9686. We'll record that as well. So you know the probability that you have a value less than 70 is 0.9686, but that is much too much because we only want between 50 and 70. So by our reasoning from previous lessons, we know we'll take the larger probability, subtract it from the smaller that we found, and when we do that, we get exactly the value in between. So here when we type this into the calculator, we will get 0.9372. So next we're asked if appropriate, which it is appropriate because of A. That was already answered above. Find the 80th percentile of our sample mean. Now, we know when we're doing this, if they ask you to find the 80th percentile, they want to find what z-score would align to give you 80% of the population before that value. So the first thing I'm going to do is I'm going to bring up the chart and I'm going to look in the area section to see where do I get closest to 0.80. So we have to look through a few values here. Okay, I think I can see where we're getting close. I think this 0.8023, 0.7995, one is closest below, one is closest above. And then between the two of them, we have to figure out who's absolutely closer. The 0.7995 is only 0.0005 away, whereas the 0.8023 is 0.0023 away. So this will be our value. And then to find the corresponding z-score, we see what row was it in? It was in the 0.8 row. What column was it in? It was in the 0.04 row. So our z-score that we're interested in is 0.84. Now, it's not enough that we have the z-score. We want to take this back in context of the problem because remember, the z-score is for the standard normal distribution, and we had transformed our normal distribution into a standard normal. So my final step will be to say this z-score came from some original value minus, now this is where we need to be careful. In calculating the z-scores for a sample of a group, we cannot use the mean. We need to use the mean sub x bar. And we don't use the standard deviation, we use the standard deviation sub x bar. And the reason I know I'm doing that here is this entire problem was we were finding the probabilities for a sample, not a random individual selected. So here, this is x minus our mu sub x bar was found to be 60 earlier. Sigma sub x bar was found to be 5.37. Now we can use algebra to get x by itself. I see I can multiply both sides by 5.37 to get rid of the fraction. Okay. And that will give me 4.5108 equals x minus 60. We will then add 60 to both sides. And this could all be done in your calculator as well. I'm just showing the work here once. So we're all on the same page. So the value that we're looking at is 64.5108. And if we were asked to round to 2 decimal places, we would round that to 64.51. And that's the data value that would be the 80th percentile of x bar. Now let's read through this next one. It says a sample size 15 will be drawn from a population with mean 125 and standard deviation of 28. Let's think about our first question. Is it appropriate to use the normal distribution to find the probabilities for x bar in this case? Take a moment to reread it and think to yourself, is it appropriate? If so, why? If no, why? Okay. What if somebody said, well, here it was a sample size of 5 and it was normal, but now we're a sample size of 15, so definitely if it's larger, then it should work. That's actually missing the point because the reason the sample size of 5 worked in the last example was it didn't work from size alone because you have to be greater than 30 to meet the cutoff, but we had this additional description that it was a normal population, and that kind of overcomes everything. However, if you read our next example closely, there's no such mention of our population being normal. It's just a population. So unless they specifically say your population's normal, you must check the cutoff of the sample size. And from our last page of notes, we know that the sample size needs to be greater than 30 for the sample to be normally distributed. So since the number of the sample is less than 30, it's not appropriate to use a normal distribution. And if it's not appropriate to use a normal distribution, then we can't find the probability of our x bar because that would rely on the normal distribution and converting it to a standard normal z-score that we could then use the chart to find. So we have to say for B, it's not appropriate. We can't solve it with what we know here. And then similarly with C, we can't find the 90th percentile because that would involve going back to our standard normal chart. And if we can't assume our sample is normal, then we can't do this as well. So this problem was pretty quick because it does not work to assume our sample population is normal because we don't meet the over 30 cutoff. Okay, in our next example, it says a sample size of 42 is drawn from a population. Now, first off, we know with the sample size being 42, that's greater than 30. So even if it's just a random population, we know by the central limit theorem, we can assume the sample is normally distributed. And we know the mean is 52, the standard deviation is 9. So our first question, is it appropriate to use the normal distribution for our x bar or sample mean? We would say yes, because we surpass the cutoff of you need to be greater than 30 sample size. However, we take note to the way the problem's worded. Since we're asked about x bar, we're asked about finding the distribution of a sample. I know I can't merely use the mean and the standard deviation given. Instead, I'm going to immediately write off to the side mu sub x bar, sigma sub x bar, so that I don't forget to calculate these. Because remember, you use the given mean and the given standard deviation if you're randomly selecting an individual, as per our previous lessons. But what we're introducing in this lesson is finding it for a sample, in which we have to find mu sub x bar, sigma sub x bar. Mu sub x bar is just mu, so that's 52. Sigma sub x bar is sigma divided by the square root of n, which for us is 9 divided by the square root of 42. We'll round that to 2 decimal places. And we see it would round to 1.39. Okay, so for B, if appropriate, find the probability that x bar will be between 53 and 54. C is, if appropriate, find the 40th percentile of x bar. Now we have done both of these types of problems in the past few minutes, so I would encourage you to pause the video now and attempt both B and C on your own. Then uncheck your work, or unpause to check your work. So use this as an opportunity to test your understanding. Now I know when I'm dealing with betweens, kind of the checklist I go through in my mind is, okay, well I have to find the z-score, and here, since I'm dealing with a sample mean, I've got to find the z-score saying the item minus the sample, or mu sub x bar divided by sigma sub x bar. Once I get both z-scores, I'll find the probability that I'm less than that value from the chart for both. And then since it's between, it's always larger probability minus smaller probability, and that's all I have to do for B. So getting started on that, let's find our z-scores. So we see it's our value 53 minus 52 divided by 1.39. We'll round to 2 decimal places, and we'll get about 0.72 when we calculate this. Now let's find the z-score for 54. When we type this into the calculator and round to 2 decimal places, we get 1.44. And now that I have the z-score, I can reference the chart for each of these z-scores and find the probability that we lie before that. So for 0.72, let's find that on our chart. And we get a 0.7642 there. Next, let's find for the z-score 1.44. And we get 0.9251. Now you'll notice I'm not drawing the standard normal curve and sketching this out like I did in previous lessons. You can continue to do that if it's helpful. By now, if we've practiced a bit, we kind of know the process intuitively and we don't need the visual help. But if drawing it is helpful to you, of course, continue to do that on your paper. So now finally, to find the between, you take the larger probability that we found and subtract that from the smaller probability, and we would get 0.1609. So next up for C, we know if it's appropriate, which it is from A, find the 45th percentile of x bar. So we know how to deal with this. The 45th percentile is basically telling me, look for what z-score takes up 0.45 area before that. So we'll bring up the chart. Now, since I'm looking for 0.45, I know at exactly 0, z-score of 0, I have 0.5 of the chart. So I need to be looking at negative z-scores, so I'll move my chart back to the first page. And I know this is probably going to be pretty close to 0 because it's quite close to the middle value of 0.5. So looking for the closest 0.45 values, it looks like these are our two contenders, and now we just have to decipher which one's actually closer. The 0.422 is 0.0022 away, whereas the 0.4483 is 0.0017 away. So that will be the closer one. So now this is our area that's closest to 0.45. We see that comes from the beginning z-score of negative 0.1. Let's figure out what column this is in by zooming out. Okay. So it came from the 0.03 column. So this is a z-score of negative 0.13 that we're looking for. And now to finish up the problem, while this z-score is the 45th percentile, we want to take things back to our original problem, which dealt with our normal distribution, not the standard normal. So I'm going to write out my z-score formula. Negative 0.13 is equal to the value I'm looking for minus my mu sub x bar, which in this case is 52 from above, divided by my sigma sub x bar, which is 1.39. And now we can use algebra to get x by itself. Solving this using our calculator, we know we would take the negative 0.13 and multiply that by 1.39. We would then add 52 to both sides, and we'll end up with this as our value. Let's round to 2 decimal places. And we get that the 45th percentile is an x value of 51.82. Now here in this next example, it's many of the same ideas we've worked with in the previous examples, except instead of just saying very dryly, the mean is this, the standard deviation is this, the sample size is this, it does the same things but in the context of a particular problem. So here, there's been a study that shows the mean distance that commuters in the United States travel each way to work is 16 miles. So mu here is 16. Assume the standard deviation is 8 miles, sigma is 8. A sample of 75 commuters is chosen. Now this is one of our keywords to indicate this particular method. We are looking at a sample of 75 commuters, so they ask us, first of all, what is the probability that the sample mean commute distance is greater than 13 miles? In order to calculate that probability, we'd have to have a normal curve that we could then translate to a standard normal that we could then use the chart. Now let's ask ourselves, does this count as a normal distribution? It doesn't say it's normal, however, my sample size 75 is greater than 30, so we know the sample mean is normally distributed. Once we verified it's normally distributed, then we can go about solving the problem. Now the first thing I'm aware of when it's asking for the probability of greater than something, I know that in the process of going to a normal curve, then a standard normal curve, then using the chart only gives you the probability that you're less than a value. So if they're asking for greater than the value, the chart's going to give me less than 13. So to translate that into greater than 13, I'm going to take that value I find from the chart and subtract it from 1. And I'm just going to personally write down a reminder here so I don't forget to do that at the end of the example. But before I can even look at the chart, I need a z-score. And since I'm dealing with the sample mean, not a randomly chosen individual, since I'm dealing with the sample mean, I need the mu sub x bar and I need the sigma sub x bar. So here our standard deviation is 8, our sample size is 75, so sigma sub x bar is 8 divided by the square root of 75. Type that into the calculator and round and you get 0.92. With this, we can now find our z-score for the value 13. So it'll be 13 minus our mu sub x bar of 16 divided by our sigma sub x bar of 0.92. Round that to 2 decimal places. And we get negative 3.26. Now that's my z-score. Let's go to the chart. So I find negative 3.0's row and then the 0.6 column. Excuse me, you can see I'm off here. I said the negative 0.30 row, but of course if it's negative 3.26, I need to go to the negative 3.2 row. Along with the 0.6 column. With that, we see the area is 0.0006. Now that would be the probability that we're less than, but the original problem cared about greater than. And again, the reason we came up with the probability less than is that's what the chart tells you. The chart always tells you the probability less than the cutoff. But if you want to translate that into greater than, remember that the whole curve together is 1. So less than plus greater than equals 1. So we can then find the probability that we're greater than by taking 1 minus the portion we don't want. And that will be equal to 0.9994. Now, our question is, would it be unusual for the sample mean distance to be greater than 19 miles? In order to solve this, I first need to find the new z-score that corresponds to 19. So that'll be 19 minus our mu sub x of 16. That gives us a positive 3.26 when rounded to 2 decimal places. Looking that up in the chart, we get our 3.2 row. Let's cross it with the 0.06 column. And when we do, we get 0.9994 as the probability that we're below that value. Now, we cared about being greater than 19. Right now, this is a probability that we're less than. So we can translate this and say 1 minus that value will give me the probability that I'm greater than, which is 0.0006. Now, what is our cutoff for being unusual? Our cutoff for being unusual is less than 0.05. And our calculated probability definitely is significantly less than 0.05. So this means it is unusual for the sample mean to be greater than 19 miles. Now, if you would, read through part C and contrast that with the wording for part B. Take note of the slight differences. In part B, when they reference the sample mean, that's our x bar. However, in part C, they're asking whether it's unusual not for the sample mean, but for a randomly chosen individual to have a commute distance greater than 19 miles. If we're back to a randomly chosen individual, we are going to use a different z-score calculation than here, because the z-score calculation that we did for the sample mean involved mu sub x bar and sigma sub x bar. However, if we're going back to the individual, we're going to use the original mean of 16 that was listed and the original sigma of 8 that was listed. So focus on those details. For the sample mean, when you do the z-score calculation, you need to first find mu sub x bar, sigma sub x bar. But if it's for a randomly chosen individual, then you can go with the original mean and standard deviation given. Now in this case, my z-score would then be 19 minus the 16, now divided by 8. Let's round that to 2 decimal places. And we get 0.38 as the z-score. Now we know the z-score chart will give me the probability that I'm less than 19 miles, but I can then turn that into a greater than 19 miles probability by saying 1 minus that. So we'll go to the chart and get the less than value first. So looking at the chart, let's highlight the 0.3 row, cross that with the 0.08 column, and we see the probability that we have a value less than 19 for a randomly selected individual is 0.6480. Okay. Now that's a probability that we're less than. Since we actually cared about greater than 19 miles, we'll do 1 minus that. And when we do so, we get 0.3520. And again, what is our cutoff for unusual? It's being less than 0.05, but this is greater than 0.05. So since it's greater, it's not unusual. So the big distinction between B and C is B cared about is it unusual for the sample mean, whereas C cared about is it unusual for the individual. So remember, what's might not be unusual for the individual might be unusual if you're looking at the sample mean as a whole. So my parting words for you in this concept is to realize in the last few lessons we've had a lot of very similar things. And your key distinction to whether you're going to work with the original mu and the original standard deviation, or if you're going to have to find new mu sub x bar, new sigma sub x bar, is whether you're dealing with selecting a random individual from the group. In that case, you stay with the original mu and the original sigma. Or if you're looking at a sample and you're trying to find For a sampled group, what's the mean? What is the probability it's less than this, greater than this, between this? So read the problems carefully, and as always, if you have questions, feel free to communicate with me via our campus communication.